Hi everyone! This video looks at a weak base titrated with a strong acid. Here, we will focus on the initial pH when 0 mils of titrant have been added. Because the titrant is at 0 mils and no reaction has occurred yet between the weak base and the titrant, we do not need a millimole table. We're just calculating the initial pH of the weak base by itself. To calculate the pH of a weak base, we must set up a reaction table. When the units are molarity, I call these mice tables. This sample mice table shows the general layout. Notice that the chemical equation at the top is for the equilibrium of a weak base having the generic formula A-. There are many different generic notations for a weak base depending on the source. I choose to use a consistent notation of A- for a conjugate base. I recognize that many weak bases are not ions, so that is one tiny glitch with this approach, in that the charge of A- may not align with the actual charge of the weak base. I feel, though, that it's easier to keep track of what's going on if we use the same generic notations consistently throughout all these titration and equilibrium problems, rather than switching back and forth. Looking at our mice table, the rows are set up as I for initial, C for change, and E for equilibrium. We will know our initial A- molarity because it's given in the problem, but the products, HA and OH- will be 0. The change that occurs with this equilibrium is that some of the A- is lost because it accepts an H+ from water, and a stoichiometric amount of HA and OH- will be gained. The terms here are all 1x because the balancing coefficients for the chemical equation are all 1. For the E row, we do the math for what is happening with the change. What you'll see is that when we solve the problem, we will initially assume that it is okay to ignore the change in x as related to the A-. Then we'll check that assumption. We cannot ignore the x's shown in the E row for HA and OH- because they're standalone x's. To calculate the pH, we'll set up our mice table like we just talked about. Then we'll solve for x, which is OH-, by ignoring the change in x. And we'll go back to make sure that our assumption was valid. Once we have OH-, then we can calculate POH by taking the negative log of the OH and pH from 14 minus POH. Our example shows that we are given 0 mils of titrant, so that tells us right away that we're looking at the initial pH of our weak base, ammonia. So we will not set up a millimole table, but we do have to set up a mice table. I will usually include the water because it reminds us of where the oxygen in the hydroxide comes from, even though we don't do anything with the water. So we have water plus our conjugate base A- going to the conjugate acid HA plus hydroxide. This is a mice table, so our units are molarity. Our rows are set up as initial, change, and equilibrium. We're starting with 0.02920 molar A-, and our initial values of HA and OH- are 0. The change is minus x for the A- and plus x for HA and OH-. The E row becomes 0.02920 minus x, x, and x. Initially, we are going to ignore this minus x, but then we'll go back and check. Because this is an equilibrium for a weak base, we need to use the mass action expression for Kb. So I'll write that out over here. Kb equals HA times OH-, those are the products, over reactants And we only include the A- because the water doesn't enter into the mass action expression because it's a pure liquid. We can then plug in the values that we have. So Kb is 1.7 times 10 to the negative 5 equals Ha, which is x, times OH minus, which is x, divided by 0.02920, because we ignored the minus x. If we cross multiply, we get 1.7 times 10 to the negative 5 times 0.02920 equals x squared. So we'll take the square root of each side, and that will allow us to solve for x. Taking a look at our sig figs, we have 2 sig figs in Kb, 4 sig figs in our molarity. So when we solve for x, we will round that to 2 sig figs. Doing the math, 1.7 times 10 to the negative 5 times 0.02920, and taking the square root of that, rounded to 2 sig figs, gives us 7.0 times 10 to the negative 4. If we take a quick look at our mice table, we see that x corresponds to the molarity of OH minus. And that is what we will use ultimately to calculate the pH. Before we do that though, we need to check the assumption. We need to make sure it was valid to ignore that change in x, and we do that by taking the x we calculated, 7.0 times 10 to the negative 4, divided by the original molarity, which is 0.02920 molar. Molarity will cancel, and when we multiply it by 100, we'll be left with units of percent. For sig figs, we have 2 sig figs in the numerator, 4 in the denominator, and the 100 is exact. So our percentage will be rounded to 2 sig figs. So doing this math, 7.0 times 10 to the negative 4 divided by 0.02920 times 100 rounded to 2 sig figs gives us 2.4%. The threshold that we set to say when is the minus x small enough is 5%. So because 2.4% is less than or equal to 5%, our assumption is valid, and we can go ahead and use the hydroxide molarity for x that we calculated. So we have 2 more steps to calculate the pH. The next step is to calculate pOH, which is the negative log of the OH. So the negative log of 7.0 times 10 to the negative 4. Looking at the sig figs, we have 2 sig figs in our log term. That will become 2 decimal places in our result. So taking the negative log of 7.0 times 10 to the negative 4 gives us 3.15 rounded to 2 decimal places. And our final calculation, I think I have room to show it, is pH equals 14.00 minus 3.15 rounded to 2 decimal places gives us 10.85.